In this video, we'll continue our discussion of topics in multiple linear regression. So we're going to talk about qualitative predictors, and this is kind of the final component that's needed to add to the conversation of multiple linear regression that really gets to show off why it is so broad and so cool. So typically, when including categorical variables in multiple linear regression, we have to go through a procedure in order to do this, and that procedure is called coding. There are several methods of coding that we can use, and we're going to focus on two in this course. The first one's going to be called dummy coding. The second one's going to be called effects coding. Now, the main idea of these are similar, but the interpretation of each of these is going to be different, and the actual process that we go through for each of them, actually the process is going to be very similar too, but it's going to have a slight difference, and actually it's going to have a somewhat major difference in interpretation just by a slight difference in the process. So no matter which coding method we use, coding splits up the categorical variable into several different independent variables that we're going to include in our model. So we're going to have one categorical independent variable, and it's going to be potentially split up depending on how many different pieces of the categorical variable there are. If there's only two different categories in the categorical variable, then we just have to include a single categorical variable in the model. Categorical variables with more than two categories require choices, and this comes because we can't include all of the categories in the model. So actually, for each of these methods, dummy coding and effects coding, there's going to be one category that can't be included. So sometimes that's called the reference category, depending on which of the methods we're using. So all of our tests would refer to that category, and sometimes it's just going to be a category that has to be excluded. Now, when we're talking about categorical variables, it's important to be able to have language to describe what we're talking about. So we're going to borrow some ANOVA language and use the terms factors and factor levels to describe these categorical variables. So the factor is going to be the variable itself. So for instance, I might talk about the factor of gender, or the factor being the hair color. This is kind of the variable. The factor levels refer to the different values that the variable can have. So for instance, gender could have male or female, or more categories if you want to go there. But however many values that variable has, the levels are those values. So when I talk about factor levels, that's what I'm talking about. For hair color, we might have three that I'm looking at in a particular study: black hair, brown hair, and blonde hair. And so I would have three different values. And I'm going to use the letter K to indicate the number of factor levels. Now, when coding a categorical variable, whether you're using dummy coding or effect coding, we'll have K-1 different independent variables that we'll include in the model to represent the one categorical factor. So we end up, as I mentioned in the previous slide, breaking up that categorical factor into K-1, where K is the number of levels, independent variables to drop into our model. All right, so first we're going to start by doing dummy and effects coding with binary independent variables, and then we'll switch over to multi-level independent variable with three levels in the factor. So dummy coding uses what are called dummy variables to drop them into the model, and uses zeros and ones to indicate the presence or absence of a particular state. So for instance, if I'm looking at the gender factor, I would pick one of the levels. So, and this may be important to write down on the side here, but if I'm looking at a factor, I'm going to pick one of the levels. If it's only a binary, if there's only two levels, I pick one of them. And then within that one, I'm going to code 1 if it is that factor level, and 0 if it's not. So in this case, I'm going to pick gender. The level that I'm going to pick is going to be female, so female is the factor level. And then I'm going to code the female variable as 1 if the participant is female, and 0 if the participant is not female or male. So my data is going to come in as gender with male and female, and then the coded independent variable is going to be called female, not gender, and then the coded independent variable is going to have a 1 anytime the individual is a female and a 0 anytime the individual is a male. Now sometimes you'll see people code the independent variable, like name the independent variable something generic and undescriptive like gender. But note if I gave you a gender variable where gender was 0 and 1, that would be extraordinarily confusing. So I try to make sure that when I'm creating coded variables, the variable names that I'm using are descriptive of what I'm measuring. In this case, I'm measuring female, 1 if you have the trait, 0 if you don't have the trait. And again, you could just as easily do this with male. If you did this with male, of course our males would be coded 1 and our females would be coded 0. You get to pick. So the model with this coding would be beta 0 plus beta 1 times female. And again, I'm dropping in this coded variable. I'm using the dummy coded variable, not the actual categorical factor. So it's important to realize that, again, when we're dropping categorical variables in the model, we have to code them, and then what actually goes in the model is not the categorical factor, it's the coded variable, in this case, the coded variable female. Now note that if female is 0, then I get my beta 0 only. 0 times beta 1 is just 0, so I get beta 0 plus epsilon. The male group, this is the model for the male group, y equals beta 0. If female is 1, I get 1 times beta 1, so my female group is beta 0 plus beta 1, and this leads to the interpretation of what these two values are. Beta 0 is the male group, so the interpretation of beta 0 is the average of the outcome for the male group, or more generally, whatever the coded factor 0 level is. And beta 1, now this is very important, beta 1 is not the average of the female group, it's the average of the male plus beta 1. So this is beta 1 actually represents how much higher or lower the female group is than the male group. So beta 1 is the increase or decrease in the dependent variable from the beta 0 level, which in our case is the male. And this is really, really important because sometimes students look at beta 1 and say, oh, this is, let's say this is weight, and I see males are, 100 pounds and females are 120 pounds or something like that. And so what we'd have is that the male group, beta 0, 100 pounds, students get this typically. But then we'd have, if females were on average 150 pounds, then I guess that's kind of backwards in it. Whatever, we'll just roll with it. Females were on average 150 pounds, then what we'd have here is beta 1 would be 50 pounds because beta 0, 100 plus 50 gives me the average weight of the female group, 150 pounds, but beta 1 is not the average weight of the female group. Beta 1 would be 50 pounds in that example. That is how much higher or lower is the female group from the male group. So it's important to realize that the test of beta 1 is a test of how much different is female from male. And beta 1 is that value, the size of the difference between female and male in the outcome. Note that this makes the test of beta 1 really convenient because if beta 1 is statistically significantly different than 0, that means that females are statistically significantly different than males. Consider if beta 1 was 0, then females and males would be the same. The change in DV from male to female, if that's 0, means that males and females aren't particularly different. So the test of beta 1 indicates, is this coded variable important? All right, and I kind of forgot I had this example, but we'll just roll with this example. So we've got the predicted y, 5 plus 3 times female, so beta 0 is 5, beta 1 is 3. So we expect the average male to have a value of 5 on the DV, and I'm just going to do generic units. The average female doesn't have 3, and again, this is an important Important point here, the average female doesn't have an outcome of 3 or a dependent variable of 3. They would have an outcome, we'd plug in 1 for female, so 5 plus 3 times 1 is 8. The average female group would be 8. And again, the actual coefficient itself, beta 1, represents the difference between males and females. And again, we test this with our normal t-test. And as a rule, the t-test of the coded variable tests against whatever the 0 factor is. In this case, 0 is males, and we end up calling males the reference group. All right, so now let's look at effects coding. Effects coding is really similar to dummy coding, but that reference category, those males, instead of being coded with zeros, now they're going to be coded with negative ones. So in our case, male is going to be the reference category, and so I have here the female dummy coded and then the female effects coded. So we've got male, male, female, female. Dummy coded, the males were zeros and females were 1. Effects coded, though, the males are going to be negative 1 and females are going to be positive 1. So the model is actually going to look the same because we still only have a single coded variable that we're going to drop in place of our categorical factor. But the interpretation, because we've now made our reference category negative 1s instead of zeros, changes. B0 now represents the average across all groups. So remember, the intercept was actually the mean outcome for the, the intercept was the mean outcome for the reference group. Now the intercept is the average outcome across all of the groups, in this case across males and females. So now if the intercept is the average across all groups, beta 1 is no longer the difference between females and males. Beta 1 is now the difference between females and the average across all groups. So beta 1 is the difference between females and beta 0, which is now the average across all groups. This is kind of weird in this particular case, but when we have more than 2 factors, it makes a little bit more sense. So again, beta 1 implies that females are going to be different than the average outcome across gender. A statistically significant beta 1 applies that. So dummy and effect coding can give very different results because they're actually talking about different things. However, when we just have 2 categories, so when there's 2 factor levels, they are going to have the same p-value in their statistical test, so that the numbers will be different, the interpretations will be different, but the p-values of the tests are going to be the same when there's just 2 factor levels in the factor that we're coding. All right, so that was the binary factor level case. Let's talk about if we have more than just 2 factor levels. So again, if we have more than 2 factor levels, we have to pick which one is going to be left out. Now in dummy coding, the one that we leave out, and we only have to leave out 1, but the one that we leave out is going to be the reference group. And what the reference group is going to be is all of the other factor levels are going to be compared to that reference group. So I'm going to use hair color, and I'll have blonde be the reference group. Now we're going to have the k-1 different coded variables that we're going to end up dropping in our model. So with the hair color, I had 3 levels of hair color. K was 3. So I'm going to end up making k-1 or 2 independent variables that I'm going to drop in. So if blonde is the one that I'm leaving out, that I'm going to have be my reference group, then the other 2 that I have left are black and brown. So I'm going to have a black variable, a brown variable, and then again, I'm not going to have a blonde variable. So black is going to be, if you have black hair, you get a 1. If you don't have black hair, you get a 0. Brown is going to be same thing, but now with brown hair instead of black hair. And again, blonde isn't going to have any of those. Now looking at the model is going to incorporate my 2 different hair colors that I included, and again there's no blonde here, but think about this. If black is 0 and brown is 0, then all that's left is beta 0. That's my blonde group. So if black and brown are 0, that is actually going to be my blonde group. So beta 0 in general is going to be the average outcome for the reference group in dummy coding. So dummy coding, beta 0 is the average outcome for the reference group. And then, because our reference group in dummy coding, all of our tests are going to compare to the reference group. Again, beta 1 is going to be how much different is black than beta 0, which is blonde. So now beta 1 is looking at the average difference in the outcome between black and blonde. And a statistical test of beta 1 says, is black hair statistically significantly on the outcome than blonde hair? Beta 2 is the exact same thing, but now comparing brown hair to blonde hair and looking at that difference, the size of that difference. So beta 2 isn't the size of the outcome for brown hair. Beta 2 is the size of the difference in the outcome between brown hair and blonde hair. And again, statistical tests of beta 2 test is brown hair different than blonde hair. Notice that this is only 2 of 3 possible pairwise comparisons we can make. We are comparing black hair to blonde hair, brown hair to blonde hair. Everything's getting compared to blonde hair, and that's why we call blonde hair our reference group, is everything compares to blonde hair. But we don't have the final comparison, the comparison between black hair and brown hair. That's not something that we have. And this is definitely a limitation of the method. Honestly, it's kind of built in, and in regression, there's not a lot we can really do. You could do something like a Tukey's test if you really wanted to follow up on this. It's an ANOVA thing. We're not going to go into that, but in terms of our statistical processes in regression, this is one of the limitations that we have in dropping in a multi-level independent variable. Now for effects coding, we're going to have similar changes as before, but the negative ones only go to the reference category, and it's a 0 everywhere else. So this is a little bit different. We're going to still use that brown hair, blonde, black, brown hair thing. But now what you'll see is that the black hair is going to be 1 for black hair. It's going to be 0 for everything else. But for blonde hair, it's going to be negative 1. So the reference category is going to be negative 1. And it's not just going to be negative 1 for one of the coded variables. It's going to be negative 1 for all of the coded variables. And this is what helps to keep that interpretation of comparing to the average across all of the categories, is that all of the categories get marked with a negative 1 for the reference group. Interpretations for effects coding are the same as before, where we're comparing each of the values that we created the coded variable for to the grand average, the average over all of the categories, not comparing each of the coded variables to the reference category. So in dummy coding, the statistical tests compared each of the coded variables to the reference category. In effects coding, we're comparing each of these to the grand average and seeing is it statistically significantly different than the overall average. All right, so that's 2 different ways to code a variable, both of which can be useful in different situations. It really depends on what you're working with. Dummy coding is really easy and tends to be the go-to for a lot of people, but sometimes effects coding can have nice interpretational properties. It really depends on your situation as to which one you could or should use. Sometimes, though, we want to test the contribution of a whole categorical factor at the same time. We don't just want to test each of its levels. Like, I don't really care if brown hair is different than blonde hair or black hair is different than blonde hair. I don't really care about the comparison to blonde hair. I just want to see, is hair color important? I want to test the whole categorical factor at the same time. Now, this is analogous from an ANOVA from your previous statistics courses, whether it's Math 116, Design of Experiments. And so when we're testing the whole categorical factor, this is an ANOVA. And actually, our strategy is to use a general linear f-test. So I want to say here, this is not ANOVA for a regression. This is one-way ANOVA, period. This is the one-way ANOVA for if you have a categorical independent variable that you learned in your previous statistics course. And again, this is why multiple linear regression is so cool, is it is ANOVA. In fact, if you remember, ANOVA, if you only have 2 factor levels, is a t-test. So multiple linear regression is actually a t-test too, if you just use a categorical independent variable with only 2 factor levels. So multiple linear regression actually statistically is exactly the same. You can run exactly the same thing as your ANOVA. You can run exactly the same thing as your t-test using a multiple linear regression framework. I will say factorial ANOVA, when you get to 2-way and 3-way ANOVA, get a little bit trickier. So take it with a grain of salt, and sometimes ANOVA has some nice the way in which ANOVA presents its results is a little bit nicer, but you can do it, and actually all of this falls into the same basic framework, that general linear model. So anyway, how do we do an ANOVA, like a honest-to-God one-way ANOVA in regression? Well, what we do is we follow that general linear f-test that I mentioned near the beginning of class. I think this was our third lecture that I mentioned this. I said we're going to come back to it. Well, hey, now we're coming back to it. So the general linear f-test, if you recall, involved creating a full model. So now we're going to, a full and a reduced model. So we're going to create the full model that has all of the different components from the categorical factors. So recall that we have those k-1 coded independent variables we dropped in the model. All of those are being included in the full model. And then we're going to create a reduced model that takes out all of them. We're not just going to take out the brown hair. We're not just going to take out black hair. We're not going to take them out one at a time. We're going to take out all of the coded independent variables that we ended up putting in our regression model from that categorical factor. So anything related to that categorical factor, that's getting pulled out. And then we do our general linear f-test to check the difference in the error. And that's it. That's the whole thing. So we just have to create a full and a reduced model, and that lets us run a one-way ANOVA, or we could do a 2-way ANOVA if we wanted to. We could do a t-test. All of that can be run using this framework and using categorical predictors. So for instance, in our case, the full model would be with the black and brown hair included, and then the reduced model would be with those k-1 coded variables dropped in the model not being included. And I would test the difference between these two models, between the full and reduced model, using the general linear f-test described in our previous lecture. Now, we talked about interactions previously. For interactions with categorical variables, nothing really changes. If we have just one categorical variable, I recommend making the interaction plot lines based on the categorical variable. So I think in the last lecture, we kind of briefly talked about how you can do it with 2 continuous variables. But if you have one of the variables as categorical anyway, then you may as well just make the different lines based on the different categories in the categorical variable. And actually with a binary categorical variable as your independent variable, it can be easier to interpret than with the 2 continuous variables, because the 2 continuous variables can, that second continuous moderator, it can be any of those values. It could be the 3 lines you make. It could be many more. It could be, there's an infinite number of values. It's continuous. So having a categorical independent variable for the creation of those plots does sometimes round it out a little bit nicer. If you've got a whole bunch of different factor levels, though, that can be a bit trickier to interpret. So if that's the case, actually categorical can be a little bit worse sometimes than dealing with just 2 continuous independent variables. But if that is the case, I would still recommend you break down the lines by the different categories in the categorical variable. Or what you could do is you could do it one way and then do it the other to see if one of the plots makes more sense to you. Now, when we're looking at interactions with categorical variables in model form, it's really important that you include interactions with all of the coded representations of the independent variable. So everything in this first parentheses is the independent variable hair color, right? These terms, black and brown, we just dropped in because we can't actually drop in a categorical variable into a regression. We have to code the categorical variable first. but these terms represent a single categorical variable that I'm interested in, hair color. A second continuous variable that I'm interested in is age. And when I want to look at the interaction between age and hair color, it's important that age gets the chance to interact not just with one of the coded components of the hair color, but with all of them. So actually, when I'm dropping in an interaction term between an interaction term involving a categorical independent variable, it's important that I make sure all of the components get multiplied together. Now, what's interesting here is if I'm looking at the interaction between two categorical variables, I have to make sure that all of the components from each one get pairwise multiplied together. So you have to look at the components from each one and make sure they all get multiplied together to look at that interaction term. Now, to test this general interaction term, I do the exact same thing as I would before. So to test the interaction between hair color and age, I'm not going to look at beta 4. I'm not going to look at beta 5. And I don't want you to get confused. These look like interaction terms, and they are, but they're just one component of the actual interaction I care about. The interaction I care about is the interaction between the overall categorical variable hair color and the overall continuous variable age. And that is not beta 4, that is not beta 5, that's actually beta 4 and beta 5 wrapped together. So to test this interaction, I would use the general linear f-test with the interaction included, and then with the interaction not included, and then compare the full and reduced models to see if the interaction contributes to the statistical model. All right, so this has been a discussion of qualitative predictors and multiple linear regression, and we have opened up the can of worms, kind of the last or one. I think that's probably the last one. There's bigger things that you can do when you get into generalized linear models, but as far as general linear models go, we've kind of opened up the last little bit of Pandora's box with our discussion of polynomial models, interaction models, and then this discussion of qualitative predictors, which gets us into modeling high-dimensional data, looking at the relationship between interactions and testing moderating effects of independent variables with one another, and then finally being able to run the statistical tests of t-tests and ANOVA within the regression framework. And then just being able to include categorical factors. We're no longer limited to having continuous independent variables. We can now have categorical independent variables and know how to treat them and know how to use them properly and know how to interpret their regression coefficients if we wanted to include categorical variables in a model. And it's very, very handy. It's very, very useful. We often have categorical variables, even if they're not of particular interest. Many of our demographic variables are categorical. So being able to include categorical variables in a multiple linear regression model is of extreme importance. In the next video, it'll probably be a little bit shorter because the last components of this are going to go pretty quick. We're not going to dive too deep into them, but we will discuss the concepts behind added variable plots and then discuss some extensions that we're not going to go into in this class, but you are welcome to check out in particular areas that are I call them alternate regression procedures, but really they're building on the foundation that we've set in multiple linear regression.